Hello, it's Keith here, and this is lesson 49 of the platform-specific series of my 68000 assembly programming tutorials. We're looking at the Genesis again this time. Now, last time we looked at porting my Mintile multi-platform tilemap to the Genesis, which was basically a simple tilemap example because the Genesis has a hardware tilemap anyway, so if you're not looking to do multi-platform code, the most interesting thing about that was it was just a basic example of how to get the tilemap working. Now, we're going to extend that example this time because last time the moving characters around the screen were actually done with the tilemap, so there was no hardware sprites. Now the Genesis has pretty powerful hardware sprites, so that seemed a shame. So what we've got today is a version you can see today where both the moving objects moving around the screen are indeed being done with hardware sprites, and you can see they've got per pixel movement and transparency because of that. So very good. So that's what we're going to look at today. We're going to look at using this example again, and what we're going to do is we're going to add the hardware sprite functionality, which is basically an alternative version of the tile drawing routines. We had draw strip and draw strip reversed for the X-flipped version. Now we're going to add an extra version this time that uses hardware sprites. So let's go over to our code and let's take a peek at that. Okay, so here is the code that we're looking at today. This Gen Mintile sprite, this is the hardware sprite version. And so what this is going to do is this is going to basically draw the moving objects with hardware sprites. Now we've got a new parameter here, HSprite number, and this is going to point to the next free hardware sprite in memory. Now basically with all of these systems, when we want to draw a large object, we need to build it up out of smaller hardware sprites. So we need to remember which hardware sprites are in use and not reuse the same ones, because a hardware sprite can't be in two places at the same time. Now in this example we're going to use 8x8 sized hardware sprites, which might not be the most efficient, but for compatibility we're just going to do it that way. If you were looking to create on all of these systems, if you're looking to create the best game for a system, you really need to go from scratch and write everything to that platform's capabilities and limitations. But if you're looking to create a multi-platform game with minimal time, minimal cost to you, then you want to try and basically minimize everything down to a lowest common denominator and work on that. And obviously that won't give you the best game possible on the Genesis. It will give you a game that you finish before you go completely insane though. So that is the choice that I'm making. It's preferable for me to finish a game than to make nothing and waste my time. Now, when it comes to drawing our objects to the screen, we're still using the same pattern data. So we had before the define patterns routine, the define tiles routine, sorry. That is transferring the tile data. It's the same tile data we're using for the hardware sprites, so nothing has changed there. Now, we had our get screen pos function before, and this was being used to calculate the position for the tilemap simulated sprites. Now, it's been modified slightly. The VRAM destination that it calculates here isn't being used by the code that's drawing the hardware sprites, but what's been changed is this version has been altered to preserve the original values of D1 and D4 in pairs of pixels logical units, because we're going to use those for the final XY coordinate of our sprite objects. Now, when we want to actually draw the sprite objects, we've got these new versions that are called by the multi-platform code. We've got do strip sprite and do strip sprite reverse, and of course the reversing is done by the hardware capabilities of the Genesis. Now what we're going to do here is kind of similar to what we did before in a lot of ways. Basically, first of all, we're going to read in our tile number from A2. It's a 1 byte tile number from our tilemap data. So we're loading that into D0, and then we're checking if we're clearing the tilemap exactly the same as before. If we are clearing the tilemap, we are clearing that byte to 0. The tilemap for the background is a cache, and any changes when they're written are set to 0 so that they're not set again. That's for the bitmap systems that are slower. Here are the hardware sprites, and the zeros in there are transparency, exactly the same as the last time. If you've not seen that, it might be worth you taking a look, but if you're just interested in how to actually work with hardware sprites, you don't really need to. Now we've got this function called get HSprite here. Now this will calculate the VRAM destination for the current hardware sprite number. So what we're going to do here is we're going to load in the next free hardware sprite number into D0 here, and we're going to multiply that by 8. You see there's 8 bytes in VRAM that define each sprite's parameters. Basically, we can see them over here. So basically we've got pairs of bytes. The first pair of bytes are the vertical position. The next pair of bytes are the width and the height and the link to the next sprite. Each sprite needs to point to the sprite afterwards in a sequence, and then the last sprite needs to point to 0 for them to draw correctly. If you forget to do that, you're going to get nothing on your screen. You'll be quite confused, or at least I was quite confused the first time. Now the next pair of bytes are things like the priority, the color palette, and the actual tile number for our sprite. and then the final pair of bytes is the horizontal position. So we've got 8 bytes in total, and they're kind of split into 4, although some bytes share parameters. The different bits do different things. So we're taking our sprite number. There's a total of 80 sprites potentially, depending on the screen resolution. I think it's 64 in some resolutions, but there's 80 in total potentially. So we're loading our sprite number into D0, multiplying it by 8 here, and then we're adding the sprite definition table data address D800. That's where the sprite data starts, so we're adding that, and the final result will be the pointer to the VRAM destination for the 8 bytes that define the current sprite number as defined by H sprite number. So if you want to modify this and use it in a different way, then this is where you would want to start copying, really. Okay. So then what we're doing here is we've got this prepare VRAM function, same as before. Basically, when we want to specify a VRAM destination address, we need to shuffle all the bits around to get it into the correct format for the Genesis. And as I said before, I believe this is a Sega Master System thing, because the Genesis VDP chip is backwards compatible with the Master System, which had far less memory, and they didn't allocate the bits in a convenient way for the larger amount of memory that the Genesis has. So we have to shift all our bits around to placate that, shall we say. So then we select the VRAM destination with VDP control. So basically you can just copy all of this for selecting a VRAM address, and this is how you would select a hardware sprite number. So that's selected our hardware sprite number. So that's what we've done there. Now, once we've got that hardware sprite in memory, what we're doing is we're incrementing the hardware sprite number by 1 here. Now, the reason we're doing that is we're going to need that in just a moment. Okay, so now we're going to transfer all of the data for this hardware sprite into VRAM. So we've got to do the V position, the Y position there, the width and the height of the sprite. Now, the 8x8 pixel sprite, those bits will be 0, and the link to the following sprite. That's important, otherwise they won't draw. We then have the priority, how it appears in front of or behind the background tiles, the color palette, the vertical and horizontal flip, and the tile number itself for this sprite. And then we've got the horizontal position, the X position there. So we're going to have to set all of those for our sprite. That's what we're doing here. So first of all, what we're doing here is we're taking our Y position in logical units. That's pairs of pixels. I use logical units as pairs of pixels. It's easier for my 8-bit systems, and so I do the same in the 16-bit systems. So we're going to convert that by doubling it. That converts it to pixels, and then we're adding an offset to center the sprite on and put it on the screen. We're then loading the resulting 16-bit Y position into VRAM by sending it to the VDP data port. Next, what we're going to do is we're going to set the width, height, and the link. Now, the link needs to point to the following sprite, and the width and the height will be 0, because it's an 8x8 sprite. And so we're loading our sprite number. We've already added 1, so effectively we're pointing now to the following sprite, and we're sending that to the VDP data port. Now, what we're doing next is we're getting back our sprite, our pattern number. We're adding A5. This is an offset to the first pattern that's been used for this tile map. The Chibico character uses a different set of patterns to the background. So we can do that there, and we're sending that to the VDP data port. We're effectively setting the palette as 0 here, and the sprite is going to be in front of the background, as we saw earlier. Okay, next what we're doing is we're calculating the X position here in very much the same way here. We're just centering that as well, and then we're sending that to the VDP data port. Okay, so that has now drawn one of our sprites to the screen, and then all we need to do is move across the screen by 4 logical units. That's 8 pixels, and that is to move us into the correct position for the next sprite. And we repeat until we've done the entire line. Once we've done the entire line, we move down 1 vertical strip by adding 4 to our Y position. 4 logical units, 8 pixels. So that's how we're doing that there. Okay. So that's how we are selecting our unflipped sprites in VRAM. Now, the flipped version, very straightforward, basically all exactly the same. The only difference is we're moving from right to left in our tile map, and we are effectively setting the horizontal flip flag. You can see this bit here is the horizontal flip flag, and we're setting that with an OR command here before we set the tile number and the other information in our X-flipped version. That's basically all there is to it. So it's pretty straightforward really using that. There is just one other thing we need to bear in mind, and it's true at any time we're working with hardware sprites. Now, hardware sprites can only be in one position on the screen at a time because of the way that hardware sprites work. Now, the problem is that as things are moving around the screen, it might be the case that we no longer need as many hardware sprites as we did before, because things might go off the screen. Now, you can see here that my sprite is no longer being drawn on the screen, but because the hardware sprites still have a position, they're still on the screen. And so what I'm doing is I'm actually removing the hardware sprites. Once I've finished, what we're doing is we're taking all the hardware sprites off the screen. Now, the way we're doing it on this system is we simply get the next hardware sprite number, and then we're setting the X and Y position of it, and we are then linking back to the first sprite number. So you can see here we're setting the link to 0 here. Now, this is slightly inefficient. Actually, what we could do is we could alter the link attribute of the last sprite that we actually defined. Here we're defining the next sprite as 0 and off screen. What we could do is actually alter the link of the last sprite, but it's simpler to do it this way, and I thought it was easier as a basic example to just set a final sprite as 0 and off screen rather than mess with the previous one. So that's what we've done there. Anyway, that's all it really takes. Hardware sprites tend to be very easy, to be honest. Once you get the hang of them, it's really just a case of firstly working out how the VRAM actually works on each system when you're working with hardware sprites, and then working within the limitations. As I say, the Genesis has a limit of 80 hardware sprites in 40 column mode, I believe, and it's 64, I think it is, in 32 column mode, and that's a fair few, but it's still relatively limited, depending on what you're trying to do, really. And as I say, I could be more efficient with this example if I was using wider and taller hardware sprites, but that would mean I would lose the compatibility with the other versions of the code, because all of the versions of the code work in 8x8 patterns when they're building their object up, and so that's why I've done that here. Anyway, though, I hope you found this useful. Go to my website, download the source code, the build script. Say, make any use of it you can. Take it apart, take the bits out of it you can, and use them in your own projects, even if they're commercial. If you can do so, use it any way you can. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.